Laplace transforms from first principles. So for Laplace transforms, we're going from a function of t in the t domain to a function of s, or in the s domain. So we're taking an equation from the t domain to the s domain. And to go from the t domain to the s domain, we use the Laplace transform. So the Laplace transform is this. If we have the function of s, that's equal to the integral between infinity and 0, integrating the function of t multiplied by the exponential to the power of minus st, all with respect to t. So the Laplace transform of the function of t will give us the function of s. Two bits to take note of, we've got s and t. Now t consists of real numbers, whereas s is a complex number, with s representing sigma plus j omega. Now that's useful to know, but that's more useful when you get into practical applications. Let's go through one example then. We have on the left here the function of time equals 4, and we want to change this into the s domain. In the top right here, you can see the Laplace transformation, which is f of s equals the integral between infinity and 0 of the function of time, which in this case is 4, multiplied by the exponential to the minus st, all with respect to t. So the function of s is the Laplace transform of the function of t. So therefore for this, the function of s is the Laplace transform of 4. We start off by using the Laplace transformation. So the function of s is equal to the integral between infinity and 0, or 0 and infinity, of the function of time, which we've stated is 4, multiplied by e to the minus st, for e to the minus st, all with respect to t. Now the important thing to note is what to do with the s and the t. You want to treat s as a constant, and you want to treat t as a variable. Looking back at our calculations, I'm going to take out that constant of 4, so we'll have f of s equals 4 lots of the integral between 0 and infinity of e to the minus st with respect to t. And now we can integrate e to the minus st. Now of integrating, just as a quick reminder, if we have e to the kx, that would differentiate to k e to the kx. So if we have e to the kx and we integrate it, it's going to be 1 over k e to the kx. So here we'll have f of s equals 4 lots of minus 1 over s, because we're treating s as a constant, so like the k here, multiplied by e to the minus st, between 0 and infinity. Now this is where it gets interesting, which if you're not a mathematician may seem weird, but what we're going to do here, because infinity isn't really a number as such, or it's not a tangible number we can deal with, so let's turn it into something tangible a, which we're going to use to input numbers into, and then we're going to see what happens with it. I'll show you what this means. So for f of s, it's equal to when the limit of when a tends towards infinity of this, of minus 1 over s, e to the minus st. Now I've changed infinity to a, but 0 stays the same. So this all multiplied by 4. So it's mostly the same as integration, except for we've changed the infinity to a. We've said, well, when the limit of a, which is this one, tends towards infinity, meaning gets closer and closer and closer to infinity, we're going to deal with what happens there. At this point in time, what I'm going to do is just ignore this 4 here, because it will make life much easier for the explanations. It will still be there, but we'll pull it back in at the end. So going about this as normal with integration, we're going to do this with the a substituted, and take away this with the 0 substituted. And the a and the 0 substitute into t, because we're treating that as our variable. So ignoring 4 for the time being, we've got minus 1 over s, multiplied by e to the minus a, take away minus 1 over s e to the minus s0. I'm going to take this right-hand side out part to explain first. Forgetting the negative, I'm just going to leave that there for the time being. So if we have 1 over s e to the minus s0. Now, even just looking at s multiplied by 0, if 0 has been multiplied by something, it's going to become 0. So this is actually the same as 1 over s multiplied by e to the 0. And we know that any number to the power of 0 is 1. So e to the 0 equals 1. 1 over s multiplied by 1 equals 1 over s. We can then pop that back into the brackets down here as minus 1 over s. Where it gets trickier for the non-classically trained mathematicians is this part in blue here. Let's pull that out now. We have 1 over s e to the minus s a. Because we've got a negative power here, I'm going to move all this into the denominator. So we actually have 1 over s e to the s a. Now it may be confusing what to do here, because we can't just input infinity. But what we can do is logically determine what will happen as this a value tends towards infinity, or gets bigger and bigger and bigger and bigger, so it's almost at the point of infinity. Because it says a tends towards infinity, so I'm going to explain it simply and nicely first. Then I'll apply it to this equation here. If we had, for instance, 1 over 2 to the power of 1, which is a half, that's going to be 0.5. Okay? If we have 1 over 2 to the power of 3, for instance, we're going to have 1 over 8, which is 0.125. So we've got a smaller number because the denominator is to a higher power, so the denominator is bigger, therefore we're getting a smaller number because 1 is being divided by a bigger number, so it's being split into smaller parts. If we then had 1 over 2 to the power of 100, which is going to be 1 over a large number, it's going to be 0.00000, probably something like that, which is an even smaller number than 0.125, which is a smaller number than that. If we had then 1 over 2 to the power of 1,000,000, for instance, we're going to have 1 over an extremely big number, which is going to be 0.00000. So many noughts it's not worth saying in this video. So it's getting closer to 0. So as this power becomes bigger, this whole denominator becomes bigger, the number becomes smaller and infinitesimally smaller. If we apply that to this expression now, so if we say a equals 1, we're going to have 1 over s e to the s, because 1s. If we say s is also equal to 1 in this instance, we're going to have approximately equal to 0.5. If we have a equals 2, we're going to have 1 over s e to the 2s. So if s was still equal to 1, we're going to have an even bigger number, which will be about 0.1, roughly, because the power the exponential is being taken to is increased, so we've got e to the power of 2s, 3s, 4s, 5s. So this denominator is increasing each time. Once we get to 100 or 1,000, we could have, say, se to 1,000 or million s, se to 1,000,000 s. We're going to be getting numbers that's closer to 0.0000000. The numbers getting smaller each time, so we're actually getting close to 0. And at this point, the bigger this a value gets, the smaller the outcome number will be. And so this outcome number will get so close, infinitesimally close to 0, the closer we get to infinity. So it's that close to 0, it's acting as if it's 0. So as a reaches infinity, this expression, or this one here, becomes so close to 0, it may as well be 0. And so we can then assume that as a hits infinity, it will be 0. Because if you have 1 over infinity, you're going to have 1 over an extremely large number equals basically 0. So we can write in this left-hand bit here that it's minus 0, or because minus and positive 0 is basically the same thing, we can just say it's 0. Now we've done all the tricky part, and we're going to pull this at 4 back into play. So we're going to add it here, so we've got 4 lots of all of this, I'm going to simplify it so it looks nicer again. So we've got 4 lots of 0 minus 1 over s equals positive 1 over s, which becomes 4 lots of 1 over s, which then simplifies down to 4 over s. So we can say the Laplace transform of 4 is 4 over s. And that's how we get Laplace by first principles. This can all be done much simpler in the next steps. But for now, here's 4 questions for you to have a go with. You can do it the exact same way we've just shown you. The third one is a bit trickier, so you may need your integration by parts knowledge. Pause the video and resume when you're ready to see the answers. The fully written answers are on my website, which is letsdomaths.co.uk. There's a link in the description below for you to go straight there. This should help give you a grounding of how to get from the t domain to the s domain and where these values all come from. We can use these values and facts to then do Laplace transformations much quicker. So that will be part of the next video in part 3 with calculating with the table. Stay safe and healthy out there, and I'll see you in the next video.